All right, we had some trouble in class here. At least I did with my pen here. So I'll give this a run here in my office. So this is just a recording of what we did in class today. Okay, so piezometers are small open-ended tubes. They're not tubs, they're tubes. They're attached to pipes, and their purpose is to read pressure. That sketch there really isn't the best. A piezometer would just be a small tube, kind of like that. And then that would fit into a larger pipe, okay? And what you're doing there is you're going to use that, look at how far the fluid goes up in the piezometer tube, and that will get you an indication of what the pressure is in the pipe. That's the idea with these, okay? So a piezometer would look like that, and then you'd look at how high the fluid goes up in the piezometer, and based on that you'll figure out the pressure in the pipe. All right, so what you do is you look at how high the fluid goes up in the piezometer, you measure that, then you just work your way back to what the pressure would be for that. So if that piezometer shown there has the water rise up to 14 feet, what we would do there, we would take 14 feet and then use that constant that we went over, the 0.433 psi per foot, and just multiply that out, and then you'd get the pressure in the pipe. Okay, so 14 times 0.433, so that's 6.06 psi is what we end up with there. Okay, so that would be the pressure in the pipe if there were a piezometer attached and the piezometer rose up 14 feet. Now, these things have limited practicality if you got large pressure changes, because the water would go up so high in the pipe. Okay, especially if it's water. So sometimes they would use fluids that had higher specific gravities than water with these. So if we had an oil with a specific gravity of 4.2, what you do, you take the pressure that was caused by the 14 feet of water, and actually if you're doing this calculation from scratch, you just kind of go like this. You'd go 14 feet times 0.433 psi per foot. That's for water, but then you say, okay, but this stuff is 4.2 times as heavy as water is. So on account of that, you'd get that pressure of 25.5 psi, okay? So that's how that would go. All right. Now, when we're on Earth here, we have atmospheric pressure, and we don't really notice this or talk about it a lot, but it's this pressure that we have around us all the time. It's caused by the weight of the atmosphere. If you look at a column of air above you, let's say, or above the Earth, that extends from the Earth up to the outer reaches of the atmosphere, a 1-inch square column weighs 14.7 pounds on average at sea level. So the atmospheric pressure generally is about 14.7 psi at sea level under average conditions. Now that A we'll get to, it means absolute. We'll come back and talk about that in a minute, okay? All right, now the higher up you go, the less air you've got over your head. So as you know, when you start at sea level, like down at Newport or something like that, it'd be 14.7 psi. As you go higher and higher, and I think I've mentioned I used to live in Flagstaff, Arizona, and that has an elevation of 7,000 feet. Well, the atmospheric pressure is quite a bit less there because there's a lot less air over Flagstaff, Arizona than there is over Newport, because Flagstaff is so much higher. Okay. Now, another thing that will happen too here with atmospheric pressure is you have weather systems coming through, high and low pressure systems that can change it too. Okay. All right, now absolute pressure is what I was just mentioning there. It includes atmospheric pressure. Gauge pressure does not, okay? So we actually talk about two types of pressure sometimes, gauge and absolute. Now, gauge pressure is the normal pressure that we're familiar with and that we use in everyday readings. So if you're talking about pressure 999 times out of 1,000, you're probably talking about gauge pressure, okay? Now, we use absolute pressure that includes the atmospheric pressure in it for certain special applications. Okay, so the relationship there is that the absolute pressure, PABS, is the gauge pressure plus the atmospheric pressure. Okay. So for an example here, let's say we're going to pump up a tire and we want to get 30 psi of useful pressure in it. What you're really doing to that tire is you're putting 44.7 psi in there. And then when that pressure there is offset by the atmospheric pressure that's pushing all around the tire. So the actual useful pressure in that tire would be the difference between 44.7 and 14.7. That would be 30 psi. So the absolute pressure under 20 feet of water, what you would do there, if you were in a lake or a tank or something and you're 20 feet down, what you would do to figure that out is you would just take the 20 feet times 0.433, and I think that's 8.66 if I'm not mistaken. So what I would do there, I'd take the 20 feet times 0.433 psi per foot, and that would come out to be 8.66 psi. But then the relationship that we have there is the absolute pressure is the gauge pressure plus the atmospheric pressure. All right. Now, what I just calculated here, if I just take 20 feet of water times 0.433, that's gauge. Okay, so what I would do here, I'd take 8.66 psi and then add the 14.7 psi to it, and then I would get the total. And what that'd be 23.36, I think. Okay, so the absolute pressure then would be the sum of those two. So it would be the 23.36 psi. Okay. Now, I just want to mention and emphasize this. This is the number that you use, like I say, 999 times out of 1,000. That's the one you work with. That's the one we focus on. I just want to mention this absolute pressure because we use it for one particular application. And I just want to introduce it, and then we'll talk about what we use it for, okay? Okay, normally we use gauge pressure, Now, absolute pressures can be used to describe what's called a vacuum. Now, what vacuum is a pressure below atmospheric pressure. Okay, on Earth, a vacuum occurs when you remove the atmosphere from an area. Examples would be using a straw to drink water. You pull the air out of the straw, you create a vacuum in the straw. Certain pumping applications, if the pump is above the water, you create a vacuum in the pump. Okay. So a vacuum has a negative gauge pressure. So if you reduce the pressure in a pipe to 3 psi below atmospheric pressure, the pressure would be minus 3 psi G, G for gauge. But it gets awkward working with negative pressures, so it's not uncommon to use absolute pressures when you're talking about vacuums. So in absolute terms, that would be minus 3 plus 14.7. That would be 11.7 psia. Okay, and that's when we really use these absolute pressures, okay, when we talk about vacuums. So you could describe that pressure as either negative 3 psi G or 11.7 psia. Now, an absolute vacuum is a complete lack of pressure. That would be a condition like in outer space. It's, you could do that here on Earth. Quite often you have to do it in a lab, but you can't create such a thing in Earth. So what you would have then would be 0 psia. That would be an absolute vacuum, which would be negative 14.7 psig. Okay, so that's what we call an absolute vacuum, just no pressure at all. Now, to measure atmospheric pressure, there's different ways. I think this was done probably in the 1600s. People started investigating this. So if you fill a tube and take a tube, fill it with water, the tube's closed at one end, turn it over and then place it in a pool of water. If it's tall enough, the water's going to drop a little bit and you're going to get a vacuum up there at the top. This is kind of like they have those self-watering dog dishes, for dogs to give them water whenever they want it. Kind of like that. That's kind of what we're doing here. Okay, so if the tube's tall enough, the water will drop a little bit. You'll get a vacuum up in the at the top. Now atmospheric pressure will work its way through that that pool and push water up the tube is what's going to happen. So atmospheric pressure is holding up a column of water. Now, if the average atmospheric pressure is 14.7 psi-A, we could look at what would happen in the tube. If that tube has an area of 1 square inch, atmospheric pressure would hold up 14.7 pounds of water in that tube. So let's have a look and see how high, what the height of a column of water with an area of 1 square inch would be if the weight of it equals 14.7 pounds. So what we're doing there, we're taking a tube with a cross-sectional area of 1 square inch, and we're going to see how high the water would rise in the tube on account of average atmospheric pressure. Okay. All right, now I've got the calculation here. It's in your book. Okay, so the volume then would be an inch by an inch, which is a 1/12 of a foot by a 1/12 of a foot by the unknown height, and when you multiply that out, that's 0.006944 H. That's the height, the volume. The weight would be the specific weight, or the density as we call it, times the volume. The density is 62.4. So when you multiply that through, you get the weight that's being held up, which is 14.7 pounds, is 0.433 H. Solve for H, it's 34 feet. So atmospheric pressure is equal to 34 feet of water. Okay, so the atmospheric pressure would hold water up in a tube, theoretically speaking, 34 feet. Okay. Now, I do need to mention that in reality, you wouldn't have a perfect vacuum up there. In a short time, you're going to have some water, some vapor pressure pushing that column down a little bit. But we'll deal with that later when we deal with pumps, okay? We'll kind of ignore that for now. So what we've got here is a number of equivalencies, things that are the same. We just found out that 14.7 psi is equivalent to 30 feet of water. If we divide that through by 14.7, we'll see that 1 psi is 2.31 feet of water. So we got 1 psi is 2.31 feet of water. We also earlier developed that 1 foot is 0.433 psi. These are just reciprocals of one another. Okay, now what we're describing here is a barometer. That's the name of this device. Now, obviously, it's a little difficult to make a barometer with water as the fluid, because it would have to be 34 feet high. So when technology advanced to the place where they were making barometers, they replaced water with mercury, because mercury is quite a bit more dense and it won't rise as high in the tube, and it's a more practical fluid to work with. Now, obviously, this stuff's very toxic, which is a real problem. But early on, they kind of lived with that and used mercury. Now, mercury has a specific gravity of 13.6. It's 13.6 times as heavy as water. So if you take the height of the water column and divide it by 13.6, you'll get the height of the mercury column, 2.5 feet, which is 30 inches. So atmospheric pressure is commonly called out as 30 inches of mercury. Now, this number can vary when high and low pressure systems move through. And if you ever watch the weather report, they'll often tell you what the atmospheric pressure is currently in inches of mercury. Okay, so what we've got here is that average atmospheric pressure can be described 3 different ways now. 14.7 psi, A, 34 feet of water, or 30 inches of mercury. Okay. So that's about what we covered today, so I think we'll call it good there.